Welcome back to the Deep Dive, where we take complex technical sources, run them through our system, and deliver the clear, actionable knowledge you need.
Today, we are focusing on what is really the true workhorse of the cloud. It's the fundamental building block that almost everything else rests on.
We're diving into Compute Engine.
We are.
That's right. For those of you taking your first steps into cloud compute, this is the launch pad. Compute Engine is essentially where you rent and run virtual machines VMs.
Right, the digital equivalent of a dedicated server you can completely control.
Exactly. We've taken your sources, everything from essential cost guidelines to, some really expert architectural blueprints. And our mission today is clear. We want to cut through the jargon, use the clearest analogies we can, and explain not just what the components are, but why.
The why is everything.
Why are specific configurations the absolute best practice for cost, performance, and of course, resilience?
And we really need to make those why statements crystal clear. Compute Engine gives you this incredible control and flexibility. I mean, it mirrors the environment you might already be used to in a traditional data center.
Sure.
But with that power comes a huge set of choices. You have to think about cost management, storage persistence, failure tolerance.
Right.
So we'll clarify those choices. Our goal is to give you the foundation you need to, really ace those essential concepts and then feel confident enough to start tackling the intermediate ones.
Okay, let's do it. Let's unpack this with our first foundational piece, the virtual machine itself.
Mm-hmm.
We hear the term VM constantly. If I'm a brand new cloud user, what exactly is a Compute Engine VM? What makes it different from me just going out and buying a physical server?
It definitely helps to use a visual analogy here. A Compute Engine VM is, well, it's like renting a highly customized, completely isolated apartment inside a massive industrial high-rise building.
And that high-rise is the Google Cloud Data Center.
Exactly. You, as the tenant, have total autonomy inside your own unit. You choose the furniture, that's your operating system, your applications, all the dependencies, and you maintain them.
Okay.
But, and this is the key part, you are relieved of all the foundational responsibility. The landlord, in this case Google Cloud, handles the electricity, the cooling, the structural maintenance, the physical security of the entire building.
So you get the dedicated environment you need, but you shed the burden of owning all that underlying physical infrastructure.
Yeah.
That concept of control without ownership.
Yeah.
That has to be what makes Compute Engine so critical.
It is, and that control is exactly why Compute Engine is the most straightforward and often the most necessary path for a really common migration strategy called lift and shift.
Lift and shift, I've heard this a lot.
Yeah.
The idea is you literally take your existing server environment and move it directly to the cloud, trying to minimize any re-engineering effort.
Precisely. And it's crucial for organizations with, legacy applications or very specific compliance needs. But even the simplest migrations can hide some really complex technical requirements.
Of course.
Our sources actually highlighted an intermediate level requirement about a Windows Server 2022 migration. Specifically, it's about when an organization wants to bring their existing licenses with them from their on-premises setup.
Right, the bring your own license model, or BYL.
Yep, BUL.
Now, why does that make this process fundamentally harder? I mean, why can't you just spin up a standard Windows VM and Compute Engine and say you're using your own license?
It comes down to the licensing terms themselves. Traditional enterprise licenses for software like Windows often require that it runs on dedicated, physically isolated hardware.
Yeah.
If you just launch a standard VM, Google Cloud is pooling resources. Your VM might be sharing a physical server with other customers, which could, technically violate your license agreement.
So we need to guarantee that physical isolation. And we need the cloud environment to recognize the specific license we're bringing.
Correct. And this requires a very specific four-step best practice. First, you create an image of your existing on-premises server. Pretty standard. Second, you import that image as a virtual disk into Compute Engine.
Okay. So far, so good.
Third, and this is the really critical technical nugget, when you import that disk or create the instance from it, you have to use a specific command line flag. OS Windows-2022 DCV.
Wait, hold on. Why is that specific flag so necessary? Wouldn't the cloud just recognize that it's a Windows image? I mean, what happens if you forget it?
That's a great question because it's a common mistake. If you forget that flag, the cloud just treats it as a standard pay-as-you-go Windows image. You risk falling out of compliance and the billing mechanism won't correctly attribute your pre-purchased license. That flag signals to Google Cloud Systems that this disk contains a licensed image that needs very specific handling.
Okay, so that handles the licensing recognition. What about the physical isolation part?
That's the final critical step. To satisfy that requirement, you must create a sole tenancy instance on Compute Engine that uses that imported disk.
Ah, sole tenancy. So that's the dedicated hardware guarantee. It's the mechanism that says this physical server is dedicated entirely to this one customer.
Exactly. It satisfies those strict licensing and compliance agreements. It's a deep integration of a technical choice driven by a legal requirement.
That makes perfect sense. Once that VM is up and running, we immediately hit the second major area for any cloud learner: cost.
Always cost.
If you are just starting out, maybe defining new business processes, and you don't yet know what your customer demand will look like, that monthly bill can be intimidating.
It's terrifying. You open the cloud calculator, you play around with some numbers, and then you realize you might have just spent hundreds of dollars testing something you forgot to turn off.
We've all been there.
Yeah.
So how do we build some organizational discipline around cost right from day one?
We start with the essential automatic levers. Every single user should know about the free tier for basic experimentation. And critically, the sustained use discounts. These are rewards the cloud provider gives you for consistent usage, and they happen automatically. You don't sign a contract for them.
So if my VM just runs for a good portion of the month,
The price per hour actually decreases the longer it runs. It's a kind of passive optimization.
so the system handles some of the technical optimization for us. But our sources highlighted that for a new organization, the best practice for cost management isn't purely technical.
Exactly. A discount is only valuable if the team is using the resources efficiently in the first place. I mean, we've all heard horror stories of a developer spinning up some massive machine for a weekend test.
And forgetting about it until Monday morning.
Exactly. The bill comes, and it's a shock. So the essential best practice for a new organization is really a two-pronged attack. You must utilize the free tier and sustained use discounts, but you have to combine that with providing mandatory training to the team about service cost management and proper instance lifecycle control.
Ah, so you're clarifying the organizational need. It's not just cloud automation. The human element is just as important.
Absolutely. Now, as the organization matures and we start to identify workloads that are stable, long-running, and critical, think about something like a deep learning training job that might take weeks and absolutely cannot be restarted.
Right, restarting would be a disaster.
Right, we graduate to the next level of savings. Committed use discounts, or CUDs.
CUDs are the commitment. You're essentially signing a contract with a cloud provider, right? For, say, 1 or 3 years, committing to a specific level of compute usage.
That's the trade-off. You sacrifice flexibility because you are obligated to pay for that compute whether you use it or not, but in return, you get the lowest possible price point for sustained, guaranteed resources.
So for that long-running, deep learning job where restarting means weeks of lost time.
Committed use discounts are absolutely the recommended option. You get maximum cost reduction while ensuring the job runs completely uninterrupted. It's guaranteed savings for guaranteed usage.
Okay, we've covered guaranteed usage. But what if a user is willing to take on a bit of measured risk for maximum cost efficiency? What if the job is truly non-critical and can withstand being, randomly terminated?
That brings us to the ultimate budget option. They used to be called preemptible VMs, and now you'll more commonly hear them referred to as spot VMs.
Spot VMs, high risk, high reward.
The definition of it, you're basically accessing the spare, unutilized capacity in the data center because Google Cloud can reclaim those resources at any time to serve a higher priority standard VM.
They give you a massive discount.
A massive discount. We're talking potential savings of up to 80% compared to standard on-demand pricing.
80% is a huge incentive. So who is the ideal customer for a spot VM? What's the perfect use case?
The ideal use case is any batch processing workload that is inherently fault-tolerant and runs for a specific manageable duration, let's say 4 hours. If the batch job is set up to resume from where it left off, and the application can handle that interruption, using spot VMs is the best way to minimize compute costs. It surpasses even the savings from sustained use discounts.
Okay, but I need to play devil's advocate here. If you're running a critical 4-hour batch job and you get preempted at hour 3, you've just wasted 3 hours of effort unless you've handled it gracefully. That sudden, violent termination, that's the risk.
And that risk is precisely why the following technical fix is absolutely essential for anyone using them. For any fault-tolerant application running on a spot VM, you must ensure it shuts down gracefully when Google Cloud sends the preemption notice.
How does Google Cloud even communicate that, hey, I'm about to pull the plug, it must be an extremely short window?
It is a very short window. We're talking seconds. Google Cloud sends a signal to the VM's internal metadata server. So the technical solution for the user is to leverage a specific metadata key. You must create a shutdown script and use it as the value for a new metadata entry with the key shutdown script. You do this in the Cloud Platform console when you're creating the instance.
So when the cloud sends that preemption signal, it automatically triggers the custom script we defined in that metadata key.
Exactly. That script is your application's final lifeline. It gives you a brief window, maybe 30 seconds, depending on the OS, to save checkpoints, write final logs, or just cleanly exit the process.
So you transform what would be an abrupt, catastrophic failure into a controlled pause.
Precisely. And that ensures that 80% cost saving is actually realized without losing all your compute progress. It's the critical step that bridges the gap between high-risk pricing and production readiness for these batch workloads.
All these cost savings are great, but the VM is useless without the data it processes. So let's talk about where that data lives. This brings us to the persistent disk, or PD. Why the name persistent? What does that really mean here?
The term persistence is absolutely key because it defines the fundamental separation between the compute power and the storage itself. Let's go back to that apartment analogy we used.
Right.
The VM is your apartment, but the persistent disk is like a leased dedicated storage unit you have downstairs in the building. It exists entirely independently of your apartment lease.
Meaning if I terminate the VM, if I move out of the apartment, the data in the PD, in that storage unit, remains intact.
Precisely. You can then launch a brand new VM instance, a replacement apartment, and just attach that existing PD storage unit to it. That separation is fundamental to cloud resilience, recovery, and scaling. It means your data is not destroyed if your compute instance fails or is retired.
That separation is great, but it also means we have a whole new layer to manage. So once we have a PD attached, we need to manage its capacity. Let's say a database is about to run out of storage space on an XT4 formatted Linux disk. The intuitive first step is to just go into the console and increase the size of the persistent disk.
And that's exactly where many new users hit an intermediate level trap. When you increase the size in the cloud console, you've successfully told the underlying cloud infrastructure, hey, I need more physical space. The storage volume grows. But the file system inside the Linux operating system, that X4 partition, is completely unaware of the change. It's still operating under its old boundaries.
So the cloud says, here's 200 more gigabytes. But the Linux OS inside the VM still sees the disk as completely full because it hasn't remapped its own file system structure.
Exactly. This requires a specific command at the operating system level to expand the file system to consume that newly provisioned space. The fix, with the least amount of downtime, is dual-layered. You must increase the size of the persistent disk in the console AND, then use the resize-tus command in Linux.
Resize-tus?
That command tells the file system to expand and use all the new capacity.
So that command, resize-tus, is the crucial handshake between the cloud control plane and the OS guest environment. It really shows that managing VMs is a technical skill that spans two distinct domains.
And this dual control concept applies directly to performance optimization, too. We saw a scenario in the sources where a database was running on an SSD persistent disk, maybe 80 gigabytes, and it needed better performance for importing these huge statistics files. The team was tempted to add more CPU, but the real bottleneck was the disk I/O.
Wait, how is disk size related to performance? I would have assumed you'd need to upgrade the disk type, not just make it bigger.
That's a really common and logical assumption, but what's fascinating here is that Compute Engine's persistent disk performance is directly tied to its provision capacity. Both the I/O operations per second IOPS and the throughput, which is how much data you can read or write per second, they scale dynamically with the disk size you choose. A small 80 gigabyte disk has a performance ceiling that is far, far lower than a 500 gigabyte disk.
So even if they only needed 80 gigabytes of actual storage space to get the speed they needed for that importing workload, they had to provision excess capacity they weren't even going to use.
That is the precise trade-off. The critical step is to dynamically resize the SSD persistent disk to a much larger size, perhaps 500 gigabytes. They pay a bit more for capacity they don't technically need, but they gain that required increase in IOPS and throughput to speed up that resource-intensive import process. It's a vital optimization technique that's often overlooked by people new to cloud storage architecture.
Performance and capacity are important, but protecting the data is paramount. Let's talk about backup strategies. For a Postgres database on a persistent disk, let's say it requires daily backups with a 90-day retention period. We want the lowest overhead approach possible. No manual scripting.
When you want low overhead and high reliability, you should always leverage cloud-native services. Manual scripts, they just become a management burden over time.
Sure, they break. Someone has to maintain them.
Right. The cloud solution here is the Backup and DR Manager, and specifically its snapshot schedule feature. The fix is simply to use the Backup and DR Manager to create a daily policy with 90-day retention. The platform handles everything: the clock, the execution, the retention lifecycle for deleting old snapshots, and the redundancy of the snapshots themselves.
That automation takes a massive operational load off the team. Okay, now let's tackle the expert level. Designing for rapid recovery during a full zonal outage. We need an application restored in another zone in the same region as quickly as possible with the latest zero-loss data.
This is where resilience gets complex. A standard persistent disk, a PD, is zonal. That means it lives in one specific zone. If that zone fails, the data is gone, or at least it's inaccessible until the zone recovers.
So to guarantee rapid failover with minimal data loss, we need storage that spans those failure domains.
And that is the regional persistent disk, or regional PD. The regional persistent disk is the breakthrough technology here. It synchronously replicates the application data across two zones within the same region. Synchronous replication is the key phrase.
What does that mean exactly?
It means that when data is written to the disk in Zone A, the transaction is not considered complete until it's confirmed to be written to Zone B as well.
So that synchronous replication guarantees consistency, but surely that adds some latency compared to a single zonal disk, right?
It does. You absolutely accept a slight, measurable increase in write latency compared to a single PD. That's because the data has to travel across that zone boundary and be confirmed in two locations. That's the resilience trade-off.
But the benefit is huge.
Immense. If Zone A fails, the data is already consistent and immediately available in Zone B.
So how did this fit into the rapid recovery architecture? What are the pieces?
The solution requires two architectural pieces working together. First, you configure the application VM using an instance template. This is your blueprint for a replacement server. Second, you use that regional persistent disk for the application data.
And when the outage hits?
If a zonal outage occurs, the template is used to spin up the application in Zone B, and that new VM instantly connects to the regional PD's volume that already lives there. This combination ensures a near-zero recovery time objective and near-zero data loss.
That regional PD is definitely the gold standard for high availability data. Let's shift back to something a bit more essential: cloning and portability. If I've spent time optimizing my Linux VM setup in, say, US Central, and now I want to deploy an exact replica in US East, maybe even under a different project, how do I move that entire machine setup cleanly across regions?
This is a classic cross-regional deployment scenario, and it requires understanding the specific utility of three cloud components: snapshots, images, and cloud storage. We can't just, copy the running VM.
I often hear people confuse snapshots and images. Let's clarify the difference here.
It's a great point to clarify. A snapshot is primarily a point-in-time recovery tool for one specific disk. It's excellent for backup. An image, however, is the full deployable blueprint for an entire system. It includes the OS, the disk structure, everything. It's what Compute Engine uses to rapidly launch new instances. That difference is critical.
Okay, so to move the whole OS, we need to convert that snapshot into a deployable image, and we need some way to carry that data globally.
Correct. The recommended three-step practice is this. Step 1, you create a snapshot of the root disk of your production VM. Step 2, you then create an image file in Google Cloud Storage from that snapshot.
Cloud storage is the key.
It's the key because it's a global service. It acts as the carrier, transporting your system blueprint across regions and even across project boundaries. Then, step 3, finally, you create a new VM instance in the US East region using that image file you stored in cloud storage as the root disk.
So snapshot the data, convert that data into a deployable blueprint, the image, and then use the global storage layer to move it. That's elegant.
It ensures portability and easy replacement. It's far superior to trying to use, manual OS utilities to copy things over.
We've established a stable, persistent, single VM, but the cloud is defined by its ability to handle immense variable load. Manually launching VMs when traffic spikes and shutting them down when demand drops it's operationally unsustainable. How does the cloud handle this variable demand elegantly?
This is where we introduce the concept of the Managed Instance Group, or MIG.
The MIG.
Think of the MIG as the self-managing automated catering crew for your application. You provide the recipe, that's your VM template, and the MIG handles all the logistics. It constantly monitors demand and ensures there is always the right number of chefs or VMs working,
So it scales up by launching new instances when load is high.
and scales down by terminating the idle ones when load drops.
A MIG is critical for stateless applications, right? Things like web servers, API layers, where any individual VM can handle any request. We had a scenario where a stateless application was running slow during peak hours. We need to automate the scaling and ensure the newly launched VMs are optimized quickly. What's the precise sequence required to set that up?
You can't just auto-scale the existing disk. You need a rapidly deployable blueprint that minimizes any startup lag. The correct intermediate sequence is 3 steps. First, you create a custom image from the existing disk.
Okay.
This image is your pre-baked, fully optimized version of the OS and the application setup. It avoids slow startup scripts. Second, you create an instance template from that custom image. This template defines the machine type, the networking, and other configurations.
And the final step.
You create an auto-scaled managed instance group from that instance template.
That explains the importance of the custom image. It bypasses that slow process of installing all your dependencies every single time a new VM is spun up under load.
Exactly. The MIG gets the signal to scale up. It needs a VM that's ready to serve traffic in seconds, not minutes. If you have a lot of OS dependencies, libraries, compilers, specific packages, the best path is to tackle that dependency installation before launch by pre-installing everything into that custom image. You then use that custom image in your instance template, ensuring every new VM is born ready.
The MIG manages the quantity of VMs. But how does it know if a VM is actually working? Or if it's just powered on and sitting there broken? This is where the health check comes in, right? The self-policing mechanism.
Health checks are the absolute lifeblood of a managed group. They determine if the application inside the VM is responding correctly, usually via an HTTP or a TCP probe. If the health check fails, the MIG assumes the VM is unhealthy and terminates it, which initiates the self-healing process.
That leads us to a classic troubleshooting problem. An auto-scaling instance group connected to a load balancer is terminating and relaunching VMs every minute. It's in this endless termination loop, even though the application itself seems fine if you test it directly. And critically, the instances lack a public IP. Why would that happen?
This is nearly always a networking issue that involves the health check itself. It's a great example of how security can inadvertently break availability. The load balancer needs to be able to probe the instance to confirm its health.
But if the instances are private, with no public IP, they're hidden deep inside the network.
Exactly. And if the firewall rules are too restrictive, the health checks, which actually originate from specific internal Google Cloud IP ranges, cannot reach the target application ports.
So the application is fine, but the monitoring system thinks it's dead because its messages are being blocked at the network edge.
Precisely. The fix is a missing firewall rule. You must ensure that a firewall rule exists to explicitly allow load balancer health checks to reach the instances in the instance group. This ensures the internal probes can pass through your security perimeter to verify the VM's health status, which breaks that cycle of termination and relaunch.
That's a perfect intermediate lesson. Cloud troubleshooting often requires understanding the communication path of the control plane, not just your application code.
Here's a related scenario, this one involving a kernel crash. An instance group has an outage. All the instances keep restarting every 5 seconds, and auto-scaling is disabled. The health check, even without auto-scaling, is still performing its self-healing function, rebooting the crashing server. A Linux expert needs SSH access to diagnose the kernel dump.
But they can't, because the machine is constantly resetting. You can't debug a machine that won't stay still. We need immediate stabilization.
The immediate critical step is to stop that self-healing cycle. You must first disable the health check for the instance group to stop the continuous restarting. This lets the crashing instance settle into its broken state, which makes it available for diagnosis.
Okay, so the reboots stop.
Only then can you add the colleague's SSH key to the project-wide SSH keys so they can securely connect to the now stable VM and run their diagnostics.
Once we achieve operational stability, we need to handle rolling updates and deployments without disrupting the user experience. Let's say we have a non-critical application update, and we specifically do not want to update any running instances. We only want new instances created by the MIG in the future to get the update. What deployment mode do we choose?
This is a really risk-averse approach. It's often used when an update is optional or maybe hasn't been fully tested in a production environment. If the new code is buggy, you don't want to force it onto your entire stable fleet. The Managed Instance Group supports this through the opportunistic update mode. The solution is to initiate a rolling update and select the opportunistic update mode.
So the running VMs just continue with the old configuration, maintaining stability, while any new VM spun up by the MIG, maybe due to a traffic spike or some scheduled maintenance, that one will receive the update.
Exactly. The existing stable VMs are untouched until they naturally replace themselves, or until you explicitly trigger a replacement later on. This provides a crucial window for testing and verification before you commit to a full fleet rollout.
Now let's jump to the expert level of reliability. Chaos engineering. Our requirement is 99.99% availability under massive, sustained user load. How do we prove that our system is truly resilient, not just fast?
Resiliency testing goes so far beyond just measuring performance under load. Chaos engineering is about deliberately introducing systemic failure to confirm that the recovery mechanisms work as they're designed. It's really the only way to test a 99.99% SLA.
So what's the rigorous expert strategy here? How do you do it?
It's a three-part process, and it's designed to break the system deliberately. First, you create synthetic random user input to mimic complex real-world usage. Second, you replay synthetic load until the autoscale logic is triggered on at least one layer, pushing the system right to its scaling limits.
Okay, so you stress the system.
Then third, while the system is under maximum stress, you introduce chaos by terminating random resources on both zones.
Whoa. So you push the system to the edge, and then you intentionally kick the legs out from underneath it by killing healthy VMs across different failure domains. If it still maintains availability, then your recovery mechanism, your auto-healing, your regional PD failover is proven.
You are confirming that the system heals itself when a component is actively dying. That is a true test of resiliency. A related, slightly less complex resiliency test we saw focused on simulating a full zone failure for an application using a regional MIG and cloud SQL. The intermediate level procedure there is to schedule a disaster simulation exercise to simply shut off all VMs in a zone and observe how the application handles the complete loss of compute capacity in that failure domain.
Moving into networking, security often mandates strict isolation. If security requires that our VMs cannot have a public IP address, meaning they live in a secure, isolated private network, how do they access external Google Cloud services, like, say, downloading installation files from cloud storage? Or how do we, the operators, SSH into them for maintenance?
This is a classic secure perimeter challenge. We need access to Google's public APIs, like storage, but without exposing our VMs to the public internet.
Let's start with that secure installation problem. Private VMs need to download installation files from cloud storage.
You must enable private Google access on the subnet where your VMs reside. This is a specialized networking capability that allows instances with only internal IP addresses to reach the external public IP addresses of Google APIs.
But how does it not use the internet?
Because the traffic never actually leaves Google's internal network. It's like a private internal route for public services.
Okay, so the correct secure method is upload the installation files to cloud storage, then configure the VM on a subnet with a private Google Access subnet, assign only an internal IP address to the VM, and then download the files using kusutl. The security boundary is maintained, but functionality is preserved.
Precisely. Now, for management access, how do we securely SSH into that private-only instance without requiring a VPN or opening a firewall hole to the world?
SSH traditionally requires an open port and an external connection, which violates that no public IP mandate.
So we shift the security perimeter, we move it from the network boundary to the user identity using Identity-Aware Proxy, or IAP. IAP shifts the security control layer to authentication. So instead of allowing connections based on an IP address, which is what firewall rules do, IAP ensures the user is authenticated via Identity and Access Management, IAM, before allowing a connection to be tunneled internally.
So what's the fix?
The fix is to configure Identity-Aware Proxy for the instance and ensure the user has the required role of IAP-secured tunnel user. Then they just use the GodCloud command line tool to SSH securely through the IAP tunnel.
That's a phenomenal capability. It realizes the principle of zero trust. Never trust the network location. Always verify the user identity. IAP completely eliminates the need for public IP exposure for basic management tasks.
Let's look at another networking challenge, this one involving hybrid environments. What if your application needs to communicate with an on-premises service, maybe a legacy mainframe, that demands extremely high throughput and low latency, way beyond what a standard VPN connection can reliably provide?
Right, a standard cloud VPN is secure and generally reliable. But since it's routing traffic over the public internet, throughput limits are lower, and latency can fluctuate based on internet congestion.
So when performance and reliable high-speed internal IP connectivity are mission critical for that hybrid setup, you have to invest in dedicated infrastructure. The solution is to bypass the public internet entirely and configure a cloud-dedicated connection between your on-premises environment and Google Cloud.
A physical connection.
A direct, private, high-bandwidth physical fiber connection.
That guaranteed physical connection would drastically minimize latency and maximize throughput, but I imagine that comes with a significant cost and provisioning time commitment compared to just spinning up a VPN.
It is a capital investment, yes, but it's the only way to meet those specific rigorous requirements for massive data transfers or extremely low latency communication that relies on internal IP addressing between the two environments.
Finally, let's address what is arguably the biggest point of friction for new cloud developers: authentication between services. If a Python script running on a VM needs to access another Google Cloud service, like BigQuery, how do we grant it permission? The script keeps failing, saying it lacks permission.
This is absolutely essential knowledge for anyone using Compute Engine. Applications in the cloud don't use personal user logins or passwords. They must use a service account.
So the VM is running the script, but the VM itself needs a defined identity that has the proper credentials to call the BigQuery API.
Exactly. Simply enabling the BigQuery API at the project level isn't enough, because the VM running the code still doesn't have the authority to use it.
So what's the fix?
The fix is multi-layered but precise. You must create a new service account with BigQuery access, assigning it only the roles necessary for BigQuery, and then execute the script with that user or account. The service account defines the application's identity and its precise permissions, enforcing the principle of least privilege. If you miss this step, the script fails, because the Compute Engine VM instance, by default, often has only very minimal access scopes.
That really clarifies that in the cloud, security is governed by identity, the service account, not just by where the traffic originates.
Exactly.
Now we enter the expert architecture section, dealing with problems that defy standard cloud solutions. We're looking at high availability for non-scalable systems and legacy requirements that rely on, outdated physical components.
Let's start with a non-scalable monolith. We have an application that has to be available 24/7, receives traffic via TCP, and crucially, does not support horizontal scaling.
Why not?
Because concurrent access to the data file system causes corruption. Downtime during an incident is acceptable, but only if recovery is guaranteed.
Wow. Okay, so if we can't use a managed instance group to scale horizontally, we can't use standard load balancing, and we need full control over the failover process. This sounds like we have to design a custom active standby pair.
Precisely. We need an unmanaged, manually controlled environment, highly resilient data, and a TCP-aware distribution mechanism. So the architecture must be active standby across different zones, which means using an unmanaged instance group. That gives us total control over the VM lifecycle.
And the data.
The data must be resilient across zones, so we require the regional persistent disk we talked about earlier. And because the traffic is TCP-based, not HTTP, the load balancer has to be a network load balancer.
So the final expert architecture uses that trifecta: an unmanaged instance group, a regional persistent disk, and a network load balancer. The failover, which I assume would be manual or scripted, would involve shutting down the primary VM and manually forcing the attachment of the regional PD to the standby VM in the working zone.
That combination ensures data consistency and allows a controlled failover for a system that fundamentally rejects the horizontal scaling paradigm of the cloud. It's a solution born from necessity, not from preference.
And speaking of necessity, let's address physical limitations. What if an enterprise legacy Windows application relies on a physical dongle, a hardware license key that cannot be virtualized? You can't just stick a USB dongle into a VM.
You've hit the wall of virtualization limits. When you need cloud benefits, speed, networking, integration, but the underlying hardware must be physically present and dedicated, the required solution is bare metal solution.
bare metal.
It provides actual dedicated physical servers located within a Google Cloud facility, connected directly to your cloud network via dedicated high-speed
It
links.
literally bridges the gap. It allows that legacy system requiring a physical key to run on dedicated infrastructure while still benefiting from the proximity and interconnectivity of the cloud.
Moving back to cost, let's look at managing mixed environments. We have production, which is 247, but we also have acceptance and development environments that are only needed during standard office hours. We need to maximize cost savings when they're idle.
We could resize the machines to a tiny configuration overnight, but compute engine costs still accrue based on the machine type and the disk size. We want deep, deep savings here.
The best practice is to entirely eliminate the compute spend during those idle times via automated lifecycle management. The recommended solution leverages two other critical cloud services. You use Cloud Scheduler to trigger a cloud function that will stop the development and acceptance environments after office hours and start them again just before office hours.
So Cloud Scheduler provides the clock trigger, and the lightweight cloud function contains the code, the gcloud commands, to manage the VM state to stop and start them.
That's the clean, serverless approach to automation. It reduces your compute spend to near zero when those environments are idle. It dramatically improves cost efficiency compared to just resizing the instances, which, as you said, still incurs CPU and memory costs.
Everything is running, automated, and secure until performance degrades. A business application suddenly becomes very slow. Where does a cloud architect look first?
The absolute first step is always the diagnostic phase, and that's powered by observability. Before you touch anything, before you reboot, before you increase the machine size, and certainly before you restore a backup, you must gather data. The absolute first step is to inspect the logs and metrics from the instances in cloud logging and cloud monitoring.
Logging and monitoring are the stethoscope for the cloud application.
Exactly. You have to identify the bottleneck. Is the CPU pegged at 100%? Is memory completely exhausted?
Okay.
Are network connections dropping? These tools tell you if it's a compute resource problem, a disk problem, or an application-level error.
Now, let's get into some deep diagnostics. If a new Linux kernel module causes batch servers to fail and the standard application logs aren't detailed enough, we need to collect specific evidence for the engineering team. What are the three distinct actions we need to take?
We need to pull information from the application, the underlying OS, and the cloud control plane all at the same time. First, use Stackdriver logging to search for the module log entries. That's collecting the application's high-level view of the failure.
Okay.
Second, and this is crucial for kernel issues, you use GCloud or the Cloud Console to connect to the serial console and observe the logs. The serial console often contains the raw kernel output and boot messages that confirm a module crash, which regular OS logs might miss entirely.
And the third?
Third, you adjust the Google Stackdriver timeline to match the failure time and observe the batch server metrics. This lets you correlate the crash time with any resource spikes or drops in CPU or memory.
Using all three cloud application logs, raw kernel data via the serial console, and resource metrics, that gives you the complete forensic picture.
Finally, let's address the expert-level mitigation scenario. A production application is dropping requests under heavy load. One process is consuming all the CPU, and the auto-scaling group has already hit its upper limit. The underlying problem needs to be diagnosed, but we need service restored right now.
The system is choking because it can't launch any new VMs to spread the load, even though the MIG knows it needs to.
The single quickest action to restore service, to inject immediate capacity and buy the engineering team time to diagnose that CPU-consuming process, is simply to increase the maximum number of instances in the auto-scaling group. This immediately gives the MIG permission to create more instances, spreading that overwhelming load across a larger fleet and hopefully alleviating the crush that's causing the request to be dropped. It's a capacity injection to stabilize the system immediately.
That was a comprehensive deep dive into the compute engine ecosystem. We began with the essentials, defining the VM through that apartment analogy and mastering foundational cost savings, including the proper application of spot VMs and that critical shutdown script metadata key.
We then elevated the conversation through intermediate territory, learning the essential two-step process for dynamically resizing persistent disks for both capacity and performance, and the lowest overhead way to handle backups via snapshot schedules. We saw how true zonal recovery depends on that key pairing of the instance template with the regional persistent disk.
We navigated the secure networking landscape, realizing that security mandates against public IPs are solved by clever routing, like private Google access for internal API downloads and identity-aware proxy for secure, identity-based SSH access.
The ultimate takeaway here is that compute engine's power really lies in its fine-grained control. But that control requires understanding the why behind every technical choice. Why use a regional persistent disk? Because the data is synchronously replicated across zones. Why use a service account? Because your application needs a secure identity to talk to other services. These concepts transform a basic user into a competent cloud architect.
We concluded with that expert case study. High availability for a single sensitive application required an unmanaged instance group with a regional persistent disk and a network load balancer, enabling a manually controlled failover mechanism.
Now, here's the final provocative thought for you to consider as you continue your deep dive into cloud architecture. If the business requirement for that sensitive application was slightly changed, if they successfully refactored the code to allow horizontal scaling, meaning multiple VMs could safely access the data concurrently, how would that single change fundamentally alter the entire architectural design we just discussed in Section 5?
Hmm.
Think about how the need for an unmanaged group and that reliance on forced disk attachment would vanish when data can be shared, and what solution would replace it.
Food for thought indeed. Thank you for joining us for this deep dive into the compute engine ecosystem. We'll see you next time.